So, welcome y'all. 2 tests down, just the final to go. I am very, very happy with how it went. Not only was the average good, but so when I look, I do look at the average in the sense of kind of how I have done and subsequent how well I've kind of prepared you all and stuff like that. So when you do well, I take that to mean I have done well. So it's a win-win for all of us. If everyone does poorly, I take that to mean I've done poorly. So to that end, really happy with this. When looking through the questions, there was only one question that less than 50% of people got correct. I won't say what that question is until next week, because I do have people still doing the people that were sick or family emergencies, the things with an excusal policy. I have people doing makeups during my office hours this week. So I'm not going to say what that question is yet, but I will tell you all next week what that is so we can make certain. And you can almost guarantee you'll see one like that then on the final. In general, so we should hopefully have a day or two before the exam to do review, and I will specifically put the questions that people didn't do well on. So those are good ones for us to review and make certain that we're cool with. Then you can almost guarantee to see those again. Because hey, well, I missed them. That means that's the area we need to kind of polish up on overall. To that end, here it is. Woohoo! 2 tests down, so the midterms are done at this point. That's 30% of your grade. That's kind of there. Reminder, the final will replace your lowest test grade if it helps you. Only if it helps you. So if your final, say you score 70% on the final, and your lowest test grade was a 60. Say test 1 was a 60. Test 1 will now turn into a 7. Okay? If your test 1 grade was an 80, your test 2 grade was also an 80, it will not replace that. It will not hurt your grade. Well, if it's lower than your current average, it'll hurt your grades. But it will not replace the lowest test grade if it is worse than both of those.
So that's averaging the multiple choice and the three results together?
Yes. Yeah, the final will replace the entire test as a whole. Yeah.
Would it be like the final replaces the grade and there's also the final, or would it just be like the test that you got final and then the final?
So then basically what I'll do is I'll just overwrite, say, let's just make up some numbers to make my life a little easier to explain. Let's say overall, your average on test 1 was a 70. Let's say overall, your average on test 2 was an 80. And let's say on the final, you score 75. Your overall average for test 1 will just turn into a 75.
Okay, so it stays 3 grades. It stays 3 grades.
Yeah. They'll say 3. I'm not going to delete it and then make the test, because that would make test 2 worth more. Yeah. I'll literally just go in and change the grade so that the average is that. Also, at the end of the semester, you will not see this. I mean, you can kind of manually calculate it yourself. At the very end, after I've done this whole grade adjustment thing, and after put everything in, I will calculate everyone's grades with and without the clicker questions, and I will take the higher of the 2. If I calculate them without the clicker questions, so the clicker questions are worth 13% or something, I forget the exact number, somewhere around that, that part will just kind of get removed and everything will kind of grow a little bit. Everything will kind of fill up that void. So, let's just pull up the syllabus so I can give you exact numbers and not get more questions. It's always good to curb that. So, boom. Go down to the syllabus and see the exact percentage I assigned to it. It wasn't a nice round number, otherwise I'd remember it. So the clicker questions are worth, look at me, good job me, 13%. So if your grade is higher without the clicker questions, which generally just means you didn't do it. If you did them, it'll be higher with the clicker questions. If it is higher without the clicker questions, everything will kind of grow to fill that 13% proportion. It'll still kind of fit the same ratios and all that kind of stuff. Nothing in particular, they all fill it up. So instead of basically your grade being evaluated out of 100 points, it's evaluated out of 87 points kind of thing. All right. And again, that's something that you can kind of manually calculate. I am not going to send anything out saying, hey, here's what happened to your grade or anything like that. This final step will be such that is the grade I will put into, so there's a place where I submit grades at the end. That's the grade I'll end up putting in. So you will not kind of see that because at that point, there's nothing I can change anyway. So just that'll kind of happen behind the scenes. Just know it will happen. And if you're curious what that would be, you can kind of manually calculate that yourself with some math. Okay, regarding the final, so this is just good to show you all any of your finals. So this isn't the syllabus. Let me just show you and prove that to you. So at the bottom, I wasn't able to add it before the class began. I was able to add it once they posted it. So it's on here as well. Friday, April 26th, and look, there it is as well. Any single one of your classes, if you just Google UCF final exams, you'll get taken to this website, and this is how I find out when your final is. I don't decide this. Every single class, their final exam period gets decided by UCF. So our exam will be Friday, April 26th, which I believe is 4 weeks from today. 3 or 4, let's see. Not today, it's Friday. From this Friday, so it'll be 1, 2, 3 weeks from this Friday. How exciting. 4 to 6:50, so it's 2 hours and 50 minutes. It's a lot of time. This test will only be multiple choice. This test will only be multiple choice because grades are literally due a week after that. So there is no way I can grade 3 response, or the grader can get 3 responses graded in a timely manner in a week. So it'll be all multiple choice. It's going to be somewhere between 40 and 50 questions. I'm currently building it right now. Time-wise, I am aiming for however long it takes this to basically be a 2-hour test. You will have the full 2 hours and 50 minutes. So make certain that's clear. You have 2 hours and 50 minutes. But time-wise, my expectation is more of like, I am timing this around a 2-hour test. Why? I don't want to give so many, doing physics and having your brain kind of be doing that for 2 hours and 50 minutes, that's a lot. That's a marathon. I do not want to test how long your mental fortitude is, we'll call it. I don't want your brain to be absolute mush by the end. So I'm kind of aiming for that 2-hour mark, which gives 50 minutes of kind of like, long story short, you should have more than enough time. More than enough time to check your work, go back, do all that kind of checks, any problems that you need to spend time on, all that kind of jazz. So you have as much time as you need. And that's ideally, if I had the ability to do this, I would give you all the same thing on any test. So much time that time is not a concern. My goal with tests is not to see if you know it in a set period of time, but the reality is we are time constrained. But for the final, really we're not. 2 hours and 50 minutes is an insane amount of time. So you will have more than enough time for this if you kind of know what you're doing. If you're going the full time, there's all sorts of reasons, and that's perfectly fine if you need the full time. But if you know what you're doing, you should be pretty comfortable time-wise with this. If you do have accommodations and things like that, please do make use of those still. So if you have accommodations through student accessibility services, time and a half, please make use of those. You even, I still want to encourage that. So there you go. Give y'all some peace of mind. This test is comprehensive, meaning it is everything. So test 1, test 2, and the stuff that we're going to be covering for the next 2 to 3 weeks. So this last chunk it's a decent chunk. Like it's meaningful. There's 2 quizzes on it. It's all circular motion stuff. So we're going to start that today. It's all things going in a circle. The energy, the momentum associated, basically take everything we've learned and just apply it to going in a circle. So we're going to learn the kinematics equations, replace it with things going in a circle. Force equations, replace it with things going in a circle. Energy equations, replace it with things going in a circle. We're going to see that basically it's just replace the variables with circle variables. So hopefully it should be hopefully fairly comfortable. It uses a lot of the same ideas, just in a different context. So, any question about the final or anything like that? Yeah. Yes, the final will be in this room. One more thing, the final, you will not have a 5x8 note card, you will have a full sheet of paper. So it's a final, so it's in everything in the class. 2 note cards is equivalent to a full sheet of paper. So you have a full sheet of, I'm not going to pass out note cards for this. I guess I could bring some blank sheets of paper, but you can probably find some of those yourself. You get a full 5, whatever, 8 by 11 inch piece of paper. Front and back. Again, don't make it a flip book. That should be more than that room to put whatever the heck you need. So there you go. You can type it all up, print it out, any of that jazz. So that's it's equivalent to 2 note cards. All right. Anything else? Cool. All right. So, moving on to what we're talking about today. We're talking about things going in a circle. That's what we're doing the next 2 weeks. Everything to do with things going in a circle. Very, very important because a lot of things go in circles. Wheels go in circles. You're like, obviously wheels go in circles. But this extends far more than just like wheels on a car. Inside a car, you've got the drivetrain. That's going in a circle. Inside generators, you've got things going in a circle. Any kind of turbine, things go in a circle. So many things go in circles, and we need to understand how things go in circles. If you just kind of look around the world, so many things have spinning parts in them. It's very, very important for our society. You can only go in a straight line so far. By going in a circle, we can basically make it more efficient. So, again, we're going to connect rotational circular things to translational. Translational being like what you were used to, velocity, acceleration, position. We're going to connect those two together. And then we're going to talk about torque and how to calculate it. So, should go pretty smoothly. Okay, so we have some definitions. So we have our axis. It's going to be what you expect. It's the thing about what you're rotating. It is important to define the axis, especially as we kind of go on. Depending on what axis you're rotating about, it's vastly different. A coin, depending on which way it's rotating, is that like there's all sorts of... This water bottle, there's 3 principal axes of rotation for most objects. So like this water bottle, like again, there's infinite numbers of ways this is rotated. Infinite axes I can rotate it. I can rotate it kind of vertically. I can rotate it kind of like a windmill. I could rotate, let's see, I did that one, and then also towards you, which there's some symmetry involved. I can also do an off-axis kind of rotation. So many ways, and that's going to affect things. And yeah, we have some connections. So arc length is kind of how much around, we're going to see that in a second. We'll see some pictures. We're going to connect that to displacement, so how far around the circle you are compared to displacement. Angular velocity, and we're going to see in a second, angular velocity is the exact same thing as angular frequency. They're the same thing. Angular velocity and angular frequency are the exact same thing. So we'll see that. We'll connect it to normal velocity, tangential velocity, and angular acceleration, and connect that to normal acceleration, tangential. So we're going to have all the equations for that, and it'll be a real fun time. I'm going to go and open iClicker because the next one's an iClicker, and it's been a week or so since we've had these. Or no longer than that. Gosh. Well, don't worry, they're back. So, well, okay, they'll be back in the next slide. So while we're waiting for it to open, all right, so arc length. We've already actually seen this at some point I've mentioned this. Arc length is the distance between 2 points along a section of a curve. So it's the arc's length. The arc's length is arc length. The variable is S. It's right there. And eventually this will open. Sadly, there's no way to show the things behind it. It's very sad. And again, we've already seen this, but it's going to be calculated by taking the angle and multiplying it by r. We are strictly in radian. Let's say strictly. We're going to be almost predominantly using radians, y'all, for circular stuff. So just make certain you kind of have that in your mind. Radians is the go-to because it lets us connect angle to distance. Kind of you travel along that circle. A really easy example of this to prove this. Well, before I say anything. No. Yeah, and a really easy way to prove this equation to you all. How many radians are in a full circle? 2 pi. If you multiply 2 pi times the radius, you got the circumference. So you can kind of prove this equation to yourself. If you're half a circle, so for a full, the circumference equals r times 2 pi. The angle being 2 pi. Half the circumference, you want half that? Oh, multiply by pi. You want a quarter of it? Multiply by pi over 4. Radians are real nice and real convenient. Oh, shocking. I didn't even have to log in. What a blessing. All right, so a piece of gum stuck to a wheel with radius 0.5 meters travels a quarter of a revolution. What distance did that gum travel? Is it 0.5 meters, 0.5 pi meters, 0.25 pi meters, or 22.5 meters? What is the distance? What is the arc length that was traveled? That is all arc length is. If a wheel is rolling, the arc length is going to be how far that wheel is rolled, assuming no slipping. We're assuming no slipping here. If it slips, then who knows? And the key here, what's the angle for a quarter of a revolution? That's the key to this problem. All right, we'll go to like 110. And 5, 4, 3, 2, 1. All right. So again, what distance did the gum travel? So this is literally going to be, the arc length is going to be the distance it travels, because as the wheel rolls, the arc length is how far it has rolled. Easy way to prove that, you can think of a wheel rotating one full revolution, and almost think of it like a piece of string that's getting unraveled. So if this was like a full piece of string and I unraveled it, that's how far a wheel will travel. Whatever. That's just good to know that every time a wheel makes one full revolution, how far does it travel? The circumference. Kind of obvious when you think about it, but it is one of those things you kind of have to think about a bit to get there. To that end, though, we're not traveling a full revolution. We're only traveling a quarter of a revolution. So our arc length, which is going to be S, is going to equal R times theta. And again, really it comes down to what's the arc length, or what's the angle? It's pi over 2. Pi over 2. 2 pi is one full revolution, so 1/4 of that is pi over 2. It is good to kind of know these things off the top of your head. We're going to be using these things a lot. Half of 0.5 is just 0.25 times pi. And we still don't want to forget our units. It is a distance. So we do have meters after all of these. Great job. Woohoo. All right. Arc length. How far things, and that's the connection between angle and distance. Now, I do want to point out something here. So arc length is kind of how far you traveled, and to get it, you multiply angle times the radius. We're going to see this again and again and again, like literally 3 times. If you want to go from like position, velocity, time to the rotational versions, you literally just take R and you multiply it by the circular version. So again, I'll mention that a few times. So if you want to go from angle to distance, multiply by R. You want to go from velocity, or you want to go from angular velocity to velocity, multiply by R. You want to go from angular acceleration to acceleration, multiply by R. We're going to see that again, again, again. I'll try to point that out. So it's pretty easy to remember once you kind of recognize that. All right, angular velocity. Look at that. I'm just going to point this out at the bottom. So velocity, you want to go from angular velocity to velocity, multiply it by R. So angular velocity is the rate of change of angle and radians per second. You've already seen this. It's angular frequency. It's the exact same thing. Angular frequency, angular velocity are 2 words that mean the exact same thing. They are the same symbol. Omega, lowercase omega. It is a vector. We're going to learn how to find the direction of it a little bit later. The direction is kind of funky. So if you kind of think about how would you define the direction of rotation, you can kind of think through why that might be funky. The unit is radians per second, ends up just being second inverse. You will often see me put it as radians per second though, because I think that's a bit more clear. It is, which is also hertz. Second inverse is also hertz, so same units before as well. The equation is the rate of change of angle with respect to time. Just like velocity is the rate of change of position with respect to time. If you understand kinematics, you'll understand rotational stuff. Just anytime you see x, replace it with theta. Anytime you see b, replace it with omega. Anytime you see a, we'll end up replacing it with alpha, which is angular acceleration. They're like one-to-one, all the same equations, all the same logic. And down here, if you're completing one full revolution and you want to figure out the angular frequency, this angular velocity, angular frequency, take how many radians are in a circle, 2 pi, divided by the time it takes for one revolution. So delta, if you just say one full revolution, what is delta theta for one revolution? 2 pi. What is the time for one revolution? Capital T, period. So this equation just comes from that. Delta theta, that theta you travel in one revolution, 2 pi. The time it takes, capital T. But again, really want to point out this down here, y'all. You want to go from angular velocity to velocity? Just multiply by r. We're going to see that again and again and again. It's a really simple conversion between the two. All right, so now we practice. A piece of gum stuck to a wheel with radius 0.5 meters travels a quarter of a revolution in 5 seconds. What is the angular velocity of the gum? And I'm going to double check my answer. I always get worried with these the first time I present them. We'll send it out and see if I regret my decision. Let's see. Yeah, it's not working. Yeah, that's what I was afraid. I was thinking like some of these were off. Give me a couple seconds. I'd love to. So, let's see. We may be blessed in this case where I just give you the answer because I think. Let's go ahead and work this one out because I think for whatever reason when I made this I may not have put it. So, what is angular velocity? We got some options. So, angular velocity is going to equal my change in angle divided by my change in time. So if we use that equation, again, I'm purposely leaving this open because I think I goofed. It travels a quarter of a revolution, same as before. So what's our pi over 2, just like before, that's our angle, divided by 5. And yeah, we should get pi over 10, which is the same as 0.1 pi. Oh, no, I did good. Good job, me. Look at that. I didn't believe in myself. You better get the right answer now. 0.1 pi. So I doubted myself, and this is what I get for it. Giving me the right answer. That's fine. I don't feel bad about it. Now, don't forget your units, though. Remember that this is rads per second, which is the same as second inverse. Not like mess it up.
So in this case, we're going multiply by r.
No, that's a great question here. So in this case, we're not. So the last one, I said, what's the arc distance? So that was kind of going from angle to tangential. In this case, we're not getting velocity. We're getting angular velocity. But that's such a good question. We should make a question based on it. So, very straightforward. Hopefully everyone gets this right. I'll close it out in 5, 4, 3, 2, 1. But yeah, it really just comes down to, just like velocity is distance divided by time, we're assuming a constant velocity, a constant rotation here. We're not speeding up or slowing down. We're not spinning faster or spinning slower. That was a really important assumption. we get this. Now, let's go ahead and take this problem. And yeah, let's change it. I'll highlight this just for posterity's sake. All right, piece of gum stuck to a wheel with radius 0.5 meters, travels a quarter revolution in 5 seconds. What is the velocity of the gum? I am going to have to change my units here. Meters per second, meters per second, meters per second, meters per second. All right, what's cool? The answer's already up there. I didn't even have to change the answers. How convenient. Ooh, no, did I? No. My goodness, I do have to change the answers. Because this is velocity. I keep doubting myself. Why? No, it's up there. I keep second guessing myself. No, oh my gosh, no. That's what you get for doing math in your head, y'all. Don't do math in your head. It's like, let's just put a bunch of zeros in front of everything. You'll never know which one's... Great, it's totally a different number now. Alright, there we go. Yeah, that's what you get for doing math in your head, y'all. You make silly mistakes. Once we get the answer, I'll tell you what silly mistake I made in my head that made me think that the answer was already up there. You can maybe guess what it is. That's a good exercise in and of itself. What silly mistake did Dr. James make? So again, it's really useful to be able to go back and forth between rotational and translational. It's a very useful skill to have. An easy case of this is how your car... I'm not 100% on this, but this is one way your car could figure out how fast you're going. If it knows how fast the tire is spinning, the angular velocity of your tire, and it knows the radius of your tire, boom, just multiply those two and you got your tangential velocity. I'm not 100% if that's the case or not, because then the question comes, what if you put a bigger tire on your car? And obviously that's going to change the calculation, and I don't think your car... I don't know if they do anything in your car if you get a bigger tire, if they do anything in the system to that. But in my mind, that's the easiest way to figure out how fast the car is going. You know the radius of the tire, you multiply it by that. But I'm not 100% on that. Something for us to look up at some point. All right, we'll close this out at 2:10. Close out in 5, 4, 3, 2, 1. All right, so fairly straightforward. Remember, if you have, so we had angular velocity from last time. You can recalculate it if you so desire. Second inverse, and the relationship between these V equals omega times R, omega being the angular velocity. Okay, so here's the boo-boo I did. You write this out, it comes down to 0.1 pi times 0.5. In my head, I'm like, oh, that's 1. 1 times 0.5 is 0.5. No, it's not. It's 0.1. That's going to shift the decimal place over 1. It's those tiny little mistakes that'll get you. So that's why, to be honest, assuming it's not just something like 2 times 3, if there's any chance you make a silly mistake, plug it in. It's not worth it to ever make a silly mistake, especially on a test or quiz or anything like that. All right, so boom, we did pretty good on this. Great job, everyone. But again, very, very useful skill. And that is a number. That would be not that fast. That'd be very, and that makes sense. This is a very slow wheel. So if you actually multiply that out, 0.05 times 3.14, that'd be 0.15 meters per second-ish. That's slow. But I mean, just read the problem and see if it makes sense. A wheel turns a quarter of a revolution in 5 seconds. That's really slow. And this wheel is not like ginormous. It's not. If this was the size of the Earth, that'd be really fast. But it's not the size of the Earth. It's a very reasonable 0.5 meters. Very slow. So our answer should be very slow. Again, it all connects. It all should make sense. All right. So this just kind of proves the derivation. Not too much to say here. Remember, x is arc length. You replace that with r, theta. R is a constant. You pull it out, d theta dt. that is angular velocity. So this is just proving to you all that velocity is r times angular velocity. I mean, you can imagine the next derivation. So eventually we're going to say, oh, acceleration. This is just a preview of what's to come. Acceleration is dv dt. Oh, v is r times omega. So r is a constant. D omega dt, we're going to learn that that's angular acceleration. So it just follows. They all kind of follow one after the other. The first one is the only one that's kind of like, where did that first equation come from? Arc length equals r theta. Literally from taking measurements of a circle. Pi is not one of those things that someone calculated per se. Pi is from a measurement. Any circle, it's just the relationship between r and the circumference. 2 pi radians, it's not like someone magically came up with that number. They literally, and you can measure this for yourself and invent 2 pi. Take a string, wrap it around a circle, find the ratio between the radius and the circumference, and you get 2 pi. So that comes from just how the world works. Pi just emerges from measurements. It's not something that they derived from anything else. It's literally just that ratio. So that's just kind of interesting. Pi is a weird thing like that. All right, so this is just a reminder, this is everything you just saw. It's nice summarized, all in one place. The arc length is r times theta, the velocity is r times omega, and there's a couple other ways to get omega to change in angle with respect to time. If you have a full circle, that's 2 pi divided by the period. Just a nice little summary slide of what we said. Nothing new up here, just a nice little summary. All right. Let's calculate the angular velocity of Earth. So, let's calculate the angular velocity of Earth. What's really interesting here, you don't need radius at all. I gave you radius. We're not going to use it. There is only one thing we need to know for this, and it's something that everyone in this room should already have memorized. If not, I will be absolutely shocked. So let's figure out what that thing is that you all have memorized without realizing it. Okay, so what are we solving for? What's given? We have the radius. I'll jot it down. We don't need it. Sometimes you have extra information you don't need, but hey, we'll still keep tabs of it. Never hurts. I'm telling you all you don't need it. You may not know that yet. So better to jot it down just in case. In general, we tend to use uppercase R for radius. Lowercase r is also fine, though. It's not like one's wrong and one's right. Okay, what else do we know? There is things we know, but right now you may not know what you need. So let's go ahead and jump to step 2 and see what we're solving for and kind of see what information we need. We want angular velocity, i.e. omega. That's a symbol for it. And we have so many equations. Let's just put all the equations. So we know that the tangential velocity of the Earth. So this is literally how fast you're traveling right now. The tangential velocity, how fast you are traveling linearly in space. That's r times omega. Great. I'm just putting them all, and we're going to decide which one we want to use. We have omega equals delta theta divided by change in time. And we have omega equals 2 pi over the period. Remember, these last two equations are basically the same equation. The last one's just a very specific case. All right. I want you all to think for a bit and say how we figure out how you would solve this. We're going to use one of those. I want you all to think and see if you can figure out which one. And what information you might need to figure that out. So I mentioned there's a piece of information you have memorized in your head. I'm going to go ahead and tell you, it's very likely not your tangential velocity on Earth. Fairly confident. I don't know what that is. If you know what that is, kudos to you. You know more than I do when it comes to the velocity of something on Earth's surface. So probably not the first one. Probably not the first one. All right, we look at the second one and we say delta theta over delta t, and we think to ourselves, okay, theta, what would I use there? And so to that end, we think, all right, what times do I know concerning the Earth? There's a really convenient amount of time that there's actually lots of options here. We could say maybe half of an Earth's revolution or a quarter of an Earth's revolution. How long does it take for the Earth to make a quarter of a revolution? Or how long does it take the Earth to make half a revolution? Or if we just jump to the last one, we can say, you know what's a really easy one? One full revolution. That's a number that you all have nicely memorized. So the angle that the Earth travels in one full revolution, that's 2 pi. That's the amount of radians in one full revolution. And t is the time it takes for the Earth to make one full revolution in seconds. And you may be like, if you know how many seconds are in your head, again, you're better than me, but I can guarantee you every single person in this room can calculate how many seconds are in a day. You just got to think about it a little bit. So, go ahead and think about that. How many seconds are in one day? How would you calculate that? I believe in your abilities to find that out. If you don't know, if you're not even figured out, once I show you, you're going to say, oh, that makes sense. You're going to have to do some math. But it is math that all of you are capable of doing. So just kind of think through that. How can I figure out how many seconds are in one day? The time it takes for the Earth to make one full loop. You can Google it, but try to calculate it. Because every one of you can. So again, probably none. If you know how many seconds are in a day, you're better than me. I don't know how many seconds are in a day. I know how many hours are in a day. Yeah.
Wait, so is this referring to the Earth itself rotating or rotating around the sun?
That's a good question. We're calculating the Earth spinning. That's a great. So the question was, are we doing how much around the Earth going around the sun or the Earth spinning? In this case, that is an important question. We're saying the axis of rotation is the Earth spinning like a top. So we're considering that angular velocity. You could make the argument of finding the angular velocity of the Earth around the sun. Different axis in that case. All right, so again, I know hopefully everyone in this room knows there's 24 hours in a day. 24 hours. Okay, well, that's not what I want. I want how many seconds. So we break it down to the next step. How many minutes are in an hour? 60. Hopefully everyone knows that. And then you break it one more step further. How many seconds are in a minute? 60. So that's how you calculate how many seconds are in a day. Hours to minutes to seconds. If you want to calculate how many seconds are in a year, every single one of you can also do that. Number of days in a year is also maybe a little iffy in terms of memorizing. 365 times 24 times whatever. It's a number. What number is this? I don't know. Let's plug it in. I don't have this memorized. 86,400. That's how many seconds are in one day. Again, if you had that memorized, kudos to you. But you didn't need to. All right, so now at this point, y'all, it's easy. 2 pi divided by 86,400. And that's going to be a small number, y'all. The angular velocity of the Earth is small. It takes a long time for it to make one circle. I mean, depending on what you define a long time as. 24 hours I consider fairly large time. So yeah, the angular acceleration is very low. And it comes out to omega equals 7.3 times 10 to the minus 5. E minus 5 radians per second. 0.000073. Okay, makes sense. If you just think about it, the radians, the amount of angle it takes every second. Now, it doesn't say to solve this, but just for funsies, let's go ahead and calculate the velocity, because this is a vastly different story. How fast each one of you is traveling tangentially on Earth's surface. So the velocity that each one of you is traveling right now on Earth's surface, everything in this room, is going to be omega times r. We have r, so hey, we get to use it. 7.3 times 10 to the minus 5 times 6.378 times 10 to the 6 And you get that every single one of you right now is traveling 463.821 meters per second. Which is wild. Remember, if you multiply that by about 2.2, that's how many miles per hour you're traveling right now. Now, again, it's all relative to what? Relative to what? Relative to something that's outside the Earth that's not rotating on the Earth. Would be kind of your reference frame. Relative to like a star, or just literally anything that's not stuck to that's not orbiting the Earth. Literally something, if something could just sit outside the Earth and watch the Earth spin, you'd be going this fast relative to that. And the natural question that people have with this is, why don't you feel like you're going this fast? Because everything's going this fast. The air around you is going this fast. The ground that you're standing on is going this fast. Remember, if you're in a car going 60 miles per hour and the road's pretty smooth, you close your eyes, you can't tell and you're not driving, you can't tell that you're going 60 miles per hour. If everything around you is going the same speed, you have no frame. The only way you can tell how fast you're going is if you have a reference. You have to have something to reference to. You stick your hand out the window, you feel the air. That's how you can tell you're going fast. But it's just good to know. You all are going real fast right now. And again, it's one of those interesting questions. Are you moving? Are you not moving? Depends on your reference frame. Right now, we consider ourselves at rest relative to everything else in the universe. No, you're not at rest. Important things, reference frames. They matter a lot. All right, y'all, last variable to introduce, and everybody kind of mentioned it. So we have angle, and then we connect that to kind of how far you go. We have velocity, and we connect that to angular velocity. We're going to have acceleration, and we're going to connect that to angular acceleration. So this is how quickly, this is whether or not your rotation is getting faster, or whether or not your rotation is getting slower. Acceleration is not whether you're spinning, it's whether you're speeding up your spinning or you're slowing down your spinning. Just like acceleration. Acceleration is not whether about you're moving, acceleration is whether you're speeding up or slowing down. In this case, though, we're spinning faster or spinning, like slowing down our spinning. And yeah, the connection to regular acceleration, just multiply it by r. The symbol here is alpha. It looks like an A. It is not an A. It is alpha, which is very easy to write. It's just this. It's an A where the top also swings up. You get nice symmetry with it. So it's like an A, but the bottom doesn't stop. I don't know.
Should your equation say alpha equals?
Yeah, thank you. Let's go ahead and put the correct Greek letter there. Fingers crossed. Oh, thank goodness. Looking for these. Oh, well, okay. So the nice thing is, fun fact for you all with equations, they're much easier to find Greek letters than the other ways that they have you do it. It is the first, you may have heard the saying alpha and omega. Alpha is the first letter of the Greek alphabet. That's where it comes from. Ironically, omega, which is angular velocity, is the last letter of the Greek alphabet. So that's just kind of interesting. So yeah, we got betas, alphas, omegas. Yeah, it's kind of funny that angular velocity is the last letter of the alphabet. And angular acceleration is the first letter of the Greek alphabet. I don't know why they did that. I'm sure there's an interesting reason, or not. I don't know. There's always a reason someone decided something. But again, very straightforward, y'all. Angular acceleration is the derivative of angular velocity with respect to time, just like acceleration is the derivative of velocity with respect to time. And how do you go from angular acceleration to regular acceleration? You multiply it by r. How did you go from angular velocity to velocity? You multiplied it by r. How did you go from angle to distance traveled? You multiplied it by r. It's a nice, easy conversion between them. And they connect logically. Just take all the things you know about linear motion and apply them to circular motion, and they'll basically all work. All right. At this point, we'll kind of see how much more we can get. 6 minutes. I don't know if I'll get to direction. We'll see. All right, let's practice. And before because I've doubted myself so much. Yeah, terrible, terrible. All right, so let's just change all the answers. Let's make this one a 24. Let's make this one an 8. Let's make this one a 24. All right. What is the equation for angular acceleration if the angular position is given by 4t cubed? So we're going from position to acceleration. So basically it's how many times you need to take a derivative. Did I? No, I'm pretty confident in this. Is it not good? No. So I give you angular position. Yeah, so we're going, just like if you're going from position to acceleration, we just put the word angular in front of it. That's all that's different about this, but the logic is the same. How would you go from an equation for position to acceleration? Do the exact same thing to go from angular position to angular acceleration. So this is the equation for angular position, i.e. the angle. Angular position is just the angle. So if you plugged in time to 4t cubed, it would give you the angle in radians. Yeah.
Maybe I'm doing it wrong, but I don't know. Oh wait. Oh, okay, no, you had to.
I did, yes. Yeah, this is one of those where my doubts were well founded this time. So I plugged all the numbers a bit. All right, great. We're looking good, y'all. So we'll go to 1:35, 10 more seconds. And the last one we'll probably do a little bit with direction, but finish it up. So 5, 4, 3, 2, 1. All right, so to kind of write this out a bit more officially, so this is theta with respect to t is 4t cubed. That's kind of the angle. Angular position is just what is my angle at some time. All right, if we want to get to omega, that's our first derivative with respect to time. So that's going to give us 12t squared. And then if we want to go to angular acceleration, that's alpha. That's going to be the derivative of omega with respect to time, which will be 24t, which again, pretty much all y'all got. So great job. And again, at any point, if I said, hey, give me the equation for how far you've traveled. So what's cool here, if you want to get how far you've traveled, it'll be 4t cubed times r. You want to get how fast you're going at some point, 12t squared times r. You want to get your angular, you want to get your acceleration, your tangential acceleration at some point, 24t times r. The conversion between them is really easy. You multiply by r. It's real nice. It's nice when things just work out like that. All right. So the last thing is to see, I think the next one is direction, I'm hoping. Because I've actually taught you all a little bit about direction. Okay, so this is going to kind of segue us into, let's see, we're not going to have the time for this, but I'm going to go ahead and tell you this is the question we're going to start next class with. So I'm not going to necessarily open it now, but something to think about. Piece of gum stuck to a tire spinning faster and faster. If the wheel is spinning clockwise and the piece of gum is on the right side, what is the direction of the net acceleration? And something to look forward to. The answer, I don't expect many people to get this one right. So I'll leave you with that as a fun one to kind of look at, figure out. Your first reaction probably won't be the right one. So we'll do this. We'll start this one next time. I'll see what you all come up with. See if you looked up anything. We'll see. But it is an interesting question.